Hello everyone, welcome to TriTea. Today we're going to solve two interesting problems, step by step. So let's begin with the first one.
While Python, C, and Java use different characters on the screen, they are often performing the exact same set of logical instructions. The underlying structure stays exactly the same. Regardless of the syntax, the processor executes the same sequence of comparisons and jumps. To see how this works, we are going to build one specific algorithm from scratch, the logic required to identify a prime number. A prime number is any whole number greater than 1 that can be exclusively divided by 1 and itself. Compare that to 4. If we divide it by 2, it splits cleanly without a remainder. Because another number worked, it fails the test. To find a prime, the computer performs a finite check. If no integer between 1 and the target can divide it cleanly, any larger number is mathematically impossible. This process of elimination proves the number's status. How do we tell a computer to check for that clean split? We use the modulo operator. Instead of giving us the division result, modulo isolates the remainder. Next, we have to define exactly which numbers to test. Our loop must isolate the integers strictly between 1 and our target number, which we will call n. If our target number n is 7, what specific numbers must the code check? The algorithm has to test 2, 3, 4, 5, and 6. If none of these produce a clean division, the number is prime. This bounded range is the engine of our logic. Let's structure this logic. Step 1, we take our target number, n. Step 2, we create a loop starting at 2 and stopping at 1 less than n. Step 3, inside the loop, we use modulo to divide n by the current number. If the remainder is exactly 0, the loop immediately stops. The number is not prime. Step 4, if the loop tests every number in our range without producing a remainder of 0, the test passes. The number is definitively prime. Now we translate the algorithm into universal pseudocode. On the left, we set n to 5 and our starting loop variable I to 2. We also create an isPrime flag and set it to true. This is our initial assumption before the testing even begins. This is a real-world Python implementation. Notice how the while x is less than n loop and the modulo break condition perfectly match the logical skeleton we just built. Let's run this code. N is 5, and our loop begins at I equals 2. Does 5 modulo 2 leave a remainder of 0? No, it leaves a remainder of 1. Because it is not 0, the code skips the break condition and increments I to 3. 5 modulo 3 leaves a remainder. 5 modulo 4 leaves a remainder. Then I increments to 5. The loop asks if 5 is strictly less than 5. That evaluates to false, terminating the loop. Because we never triggered the 0 remainder trap, our isPrime variable survived as true. 5 is a prime number. Let's test a non-prime number. We set n to 4 and reset our loop variable to 2. On the very first iteration, we run 4 modulo 2. This divides perfectly, resulting in a remainder of exactly 0. That 0 remainder triggers the next line of code. The isPrime flag flips to false, and the break command immediately stops the loop. We have seen the same logic execute in Python and in our generic model. While the syntax changes from one environment to the next, the path from input to result remains constant.
Now let's see how the code looks in C. In Java, in Python, Let's now move to the second one.
Here is a clear diagram showing the number 13 in our standard human counting system, base 10. Right next to it is its exact equivalent in computer language, base 2, represented as a sequence of ones and zeros, 1, 1, 0, 1. We can actually map that same base 10 number to other counting systems as well. We can convert it to 15 in base 8 or the letter D in base 16. To get from base 10 to any of these targets, there is one universal mathematical rule. You continuously divide your starting number by your target base. To reach base 2, you divide by 2. To reach base 8, you divide by 8, and so on, extracting the remainders along the way. Programming languages have very different syntax rules, but this underlying mathematical logic for base conversion remains exactly the same whether you're writing in Python, Java, or C. This brings us to a clear set of algorithm steps. Step 1 is simply our starting gate. We take our original number and verify that it is strictly greater than 0. If it is, we proceed. Next, we divide that number by 2 and isolate the remainder. Because we are dividing by 2, that remainder will mathematically always be either a 0 or a 1. We take that specific 0 or 1 and capture it. This becomes the very next digit in our resulting binary sequence. Then, we update our starting number. We do this by taking the integer quotient of the division we just performed, discarding any fractions, and making that our new working number. We repeat this entire loop until our working number hits 0. Once we finish, we take our sequence of extracted remainders and read them in exact reverse order. Let's test this before writing any code. If your starting number is 13, what are the exact integer quotient and remainder when you divide it by 2? Take a second to calculate that mentally. Breaking a problem into plain English steps strips away distractions. It allows you to focus purely on the logical flow before you ever have to worry about missing semicolons or specific language syntax. Here is a split view showing how English logic maps directly into a standard while loop. On the left, we have our code structure using variables for number, remainder, and string. On the right, we have an empty dry run table to track those variables. Pay close attention to this specific line. Binary equals remainder plus binary. By appending the new remainder to the front of our existing string, the code automatically solves the issue of having to read the sequence backwards later. Let's dry run this starting with 13. 13 is greater than 0, so we divide by 2. The remainder is 1, so we update our string to 1. The integer quotient is 6, so 6 becomes our new n. Moving to loop 2, 6 is greater than 0. We divide by 2. The remainder is 0. We push that 0 to the front of our string, making it 0, 1. The integer quotient is 3. On loop 3, n is 3. The remainder of 3 divided by 2 is 1. We push that 1 to the front, updating our string to 1, 0, 1. The new integer quotient is 1. Finally, loop 4, n is 1. 1 divided by 2 gives a remainder of 1. We attach that to the front, giving us 1, 1, 0, 1. The integer quotient here is 0. When the loop checks its condition again, n is exactly 0. It is no longer greater than 0, so the loop terminates immediately, leaving us with our final, correct binary string. By grasping this specific loop structure and string manipulation, you can solve this conversion problem in Java, C, or Python. The syntax will change, but the logical flow never does.
Now let's see how the code looks in C. In Java, in Python, Comparing all three languages, C, Java, and Python, we can clearly see how the core logic is same in each three. Just syntax is the one which changes. Thank you for watching. See you in the next video.
Subscribe now.